Good afternoon, everybody, and welcome to this week's Energy Symposium. As we usually talk, next week we're going to have Professor Kevin Weaver. Kevin is the chief scientist for TerraPower, which is a small modular reactor company in the startup phase that we're located in Washington State. He'll come talk to us about not just their design for TerraPower for a small modular reactor, but basically all Gen 3 and Gen 4 small modular reactor designs that are being pursued, not only nationwide but worldwide today. So I think it'll be a very interesting talk if you're interested in that type of technology. I met him this summer at a conference in DC. Very knowledgeable individual, gives a very good presentation. So if you're hoping there's a nuclear renaissance or a future for nuclear power in the U.S. aside from Vogtle 3 and 4 or those projects, and you're interested in SMRs, I really encourage you to come next week and listen to that one. Today we have the distinct pleasure of having Professor Dave Nagel with us. Dave is from George Washington University. Or is it the University of George Washington?
George Washington.
George Washington University, located in Washington, D.C. He's got quite a storied career. I have a soft spot in my heart for him because he's a Navy ROTC man like myself, and he's had a long and distinguished career. He got his start with a BS in Engineering Science at the University of Notre Dame, and then an MS in Physics and a PhD in Materials Engineering from the University of Maryland. He's worked at the Naval Research Lab in Washington, D.C. for quite some time, as well as being affiliated with the Office of Naval Research in Washington, D.C. You've got his bio there if you'd like to read all of it. It goes on and on. He's had quite a distinguished career. But the reason I invited Dave is he is heavily involved these days in a technology that I've always had a soft spot for, low-energy nuclear reactions, formerly known as cold fusion. If you all remember Fleshman and Pons about 2 decades ago, or is it 3 decades ago now?
Wow.
This has become a somewhat controversial topic, or at least was at the time. I think some of the controversy has died down, but the technology has not died down. I like things that are controversial. This is important. So Dave is either a charlatan, or he is at the cutting edge of science and as we understand it. And I'll let you make your own decision on whether what he presents here is sound science or something else. I vote for the sound science, but for those of you who aren't familiar with LENR, unfortunately it doesn't fit the standard chemistry model in the world of chemistry, and it doesn't fit the standard physics model of nuclear physics. What's happening seems to be somewhere in between, which means both schools of thought put it at arm's length, which means there's very little work being done, certainly not enough work being done in this field, and those who do work in this field are looked at somewhat askance sometimes. As I think you'll see from Dave's presentation, there is some very real science going on here. There's some really real phenomena going on here, and like things that people don't understand, it's very interesting. So I think we're probably kind of on the cutting edge of something here, and we'll see what it does. Dave, I'll turn it over to you. We've got about 60 minutes, and if you would, just leave a few minutes for questions. And as always, if any of you want to join us afterwards, I think we're going to go over to the AT&T Center to Gabriel's and have some libations and some food afterwards. So please join us afterwards if you'd like to continue the discussion on a one-on-one basis.
Well, thank you, Fred. I appreciate the invitation and the introduction. I came down here maybe 30 years ago to work on a hot fusion project. Texas Tokamak was an active spectroscopist at the time, so now I'm down here at a very different situation and a very different time. So will you pass out slips so people can vote on the way out?
Absolutely.
Okay, fine, and you can see what they think of this. So as you heard, I worked a long time for the Navy, and then I went to SEAS, the School of Engineering and Applied Sciences, and I have a consulting company because people are interested in this area, and I try to support that interest. So let's see, I do like this, yeah. So this is a 2x2 matrix. I talk about the status and the prospects of the science and the business of LENR. I don't have a laser pointer that works, but I hope you can follow things. So as far as the science is concerned, there is a very solid empirical database over almost 3 decades that it is possible to produce nuclear reactions using chemical energies. Okay, so I meet you in Starbucks 2 weeks from now or a month from now or someplace in Washington, and I say, okay, what's the essence of this field? That's the answer I'm looking for. You can produce nuclear reactions using chemical energies. You don't have to go to high energies or high temperatures. Now, the prospects of the science, somebody's going to figure this out. Okay, I'll say later, there are lots of theories, none of them have been adequately developed. So there's a scientific plum sitting here. And I'm one of many people who are trying to figure out just what is going on here. Why is it possible? Now, when you go to the business aspect, there are over 20 companies in 9 countries who are trying to develop products based on this technology, this emerging technology, even though we don't understand it, which is a rather interesting situation. One of the things I'll touch on later is there's a problem with reproducibility. So some people say, well, we used fire before we understood it. Yeah, but it was reproducible. And you could control it, you know. We're in a different situation. We don't have that. So a colleague and I, looking ahead, feel that there is going to be an industry emerge from this technology. We formed a corporation, an industrial corporation called Low Energy Nuclear Reaction Industrial Association. A couple of years ago, we published a calendar that shows the work in many countries, many people and so forth. So I have some copies of this if anybody would like to pick up one on the way out. I'd appreciate it. So exciting new science, big riddle to solve, and I will tell you more that it has great practical promise as a clean energy source. Okay, so what if we already understood the science? We still have this. Okay, what if there were no promise? It was an esoteric study. It's still a nice scientific problem. Okay, so I'm literally excited to be involved in a subject that has these two facets. It's a lot of fun. Okay, so the outline of the talk says we're going to address the issues of operability and utility, and we're going to do it by looking at two things: reaction products and heat that come out of these reactions. So you look at the reaction products. I will show you data on the production of tritium, helium, and other elements, transmutation products. Okay? Alchemy, by another name. Okay? And the heat values that come out of these experiments, high ratios of the energy out to the electrical energy that's put in, thermal out divided by electrical in. High ratios. Okay, talk more about that. And if you take the total energy that comes out of the experiment divided by the number of atoms in the experiment, you get values that are as high as 2 kilo electron volts per atom. Far, far higher than can be explained by chemistry. Okay? Now, reaction products, will they be of use? Probably not. Okay? The rates are too slow. You know, I've got friends who say, I'm going to make platinum, make money. Now I have friends who say, I'm going to remediate nuclear waste. No. Okay? So I don't think there's going to be much on that side of the house. But there is great potential for both civilian and military applications of the heat that comes out of LENR. So the high-level view is we're seeking understanding. Yes, they occur, but they're not understood. And we're seeking exploitation, that is practical use of them. Many attractive features, but there's a long way to go to commercialization. Okay? And I can talk as much as you like about that. And by the way, I almost forgot to say, any question, anytime. Okay? This talk is for you. If you don't get out of this talk what you want, it's not entirely my fault. Okay? So please, if you want to interrupt with questions, I would welcome that. A dialogue is the best. So the outline is we're going to talk about the operability, the yellow part here, and then the heat, the scientific part of the heat, and then the potential. So the talk has two parts. We'll talk about the evidence for the reality, and then we'll talk about prospects of commercialization. And again, this twofer, this duality. Now, if anybody looks at this field, there's an immediate problem. Too much information. Thousands of papers describing many experiments, all kinds of results. So this is a one-view graph attempt to organize the information that's available in the field. Readily available. It's on the internet. It's all over the place. Okay? If you want to look into it, I can give you many links in order to get your arms around the information here. So either protons, hydrogen, or deuterons, deuterium, are put together with metals. The process is called loading, and then measurements happen. Okay? So these are the sources of the protons and the deuterons, liquids, gases, plasmas, beams, and they're brought together by electrochemical or thermodynamic or kinetic purposes. The materials involved, palladium or alloys with deuterium mainly, but also hydrogen. Nickel and its alloys with hydrogen mainly, but also deuterium. Other things, that's what comes together. And the measurements fall into a variety of classes indicated here. Heat measurements, nuclear product measurements, A few experiments have shown energetic particles coming out, okay? And then there are some low energy emission experiments. So the initial work by Fleischmann and Pons, which was reported in a press conference in Utah in 1989, involved palladium and deuterium and heat measurements mainly, okay? And there are other things, and I will go through these during the course of the talk. Okay, so remind you of some very, very basic facts about hydrogen. It has 3 isotopes: protium, no neutron; deuterium, 1 neutron; tritium, 2 neutrons. These go into experiments. This comes out of some experiments. This is a radioactive element, okay? Doesn't appear in the environment. Now, we're talking about what used to be called cold fusion. Many of you know about hot fusion, okay? So let's take a moment to look at conventional, collisional, hot thermonuclear fusion, DD fusion. So if you slam deuterons together in a beam or in a plasma at high temperatures, 100 million degrees, high temperatures, can only be contained in magnetic bottles. They're very, very demanding. You will get out half the time tritium and a proton, or helium-3 and a neutron with these energies. And then a part in 10 to the 7th of the times you get a helium and a gamma ray with around 24 MeV. Ask you to remember the 24 MeV. Okay, it'll come in later in the talk. Okay, so that's what we're comparing against. So when this field burst on the scene, you know, it was on the cover of Time and Newsweek and Business, U.S. Business News Report in 1989, 40 days after the announcement. Burst on the scene. People say, fusion, we'll look for these things. So people have sought to measure tritium, helium-3, neutrons, the things in red there. Okay, lots and lots of experiments have done that. Okay, so part 1, evidence for the reality of LENR, falls into these categories, and I will walk through in sequence: tritium, helium, 1 view graph on other elements, and then get into the heat data. So I'll give examples. Now, I am going to do you a disservice. I'm going to show you 8 or 10 data graphs, okay, that deal with the subject, these topics, without going into enough detail, okay? So I'm not out to convince you of the reality of LENR. Only if you want to be convinced about this, you have to look at the literature. You have to examine the reputations of the people who published the papers, the calibrations, the equipment they used. It's a lot of work. So I'm just going to show you the proverbial tip of the iceberg of some of the best evidence for these various things. So let's start with tritium. Electrochemical experiment, little beaker, bubbling away, voltage in, okay. And this was done by John Bockras's group at Texas A&M at the time. And they measured the tritium activity, DPM, disintegrations per minute per milliliter, time across here, and it builds up. Now, the 2 arrows with the D2O is they added more heavy water to make up for the heavy water that had been lost to electrolysis, okay. And you know, one time it didn't seem to make a difference, one time it did make a difference, but it went up, okay? So, you know, Bockras was one of the top 2 electrochemists in the world at that time, along with Martin Fleischmann. Skilled, multiple instruments, lots of blanks. If you look at his paper, it's a very thorough scientific study, well done, well reported, with good people, good equipment, calibrations, yada, yada. And there's the data. And so in a 1996 paper, 7 years after the Fleischmann-Pons announcement, Bockras wrote production of tritium to 100 published confirmations, okay? So there was a lot of information available on this field very, very, very early in the field, in the 90s, okay, within a decade of the announcement. Okay, let's stay on tritium and switch to an experiment that was done by Tom Claytor and his colleagues at Los Alamos. So they had a circulatory gas system. You see the gas flow loop on the top there. And over on the right, they had a plasma cell, little cell with a palladium wire in it and an atmosphere of deuterium, and they applied a voltage. They got a glow discharge, like a fluorescent tube. Okay. And the gas went through that femtotech tritium gauge up at the top there, and they were able to plot the reading as a function of time. And sometimes it didn't work. Some materials did not activate, did not produce any tritium, but other times they got it. Now, there's a lot of detail here. They did various things and you had jumps in it. I'm not going to go into that. I invite you to look at the paper if you're interested. But when you look at this as data, you know, this isn't noisy data where you're barely able to discern a signal. This is good signal to noise ratio. Okay? Now, that same group had the ability to tap the gas off the lower part of their system, burn it, and then take it to an entirely different instrument, a scintillation counter, and measure the activity, and they got the same answer. Okay, so here are two independent measurements in the same experiment by very competent people at a national lab. Okay, hard to get rid of. In fact, if I'm in a feisty mood, I will defy people to make this data go away. You know, it's really, really, really strong data on the appearance of tritium. Okay, you say, well, I've been waiting for helium. Okay, here's helium data. This was done by a team in Japan, Arata. He got the equivalent of a National Medal of Science twice from the emperor. I mean, this is no slouch. This is a guy playing at a very, very high level. So he took a cylinder of palladium, and he drilled out a hole and welded a cap on it. And he made that the cathode in an electrochemical system. So the deuterium permeated into the palladium. Palladium soaks up deuterium and hydrogen like crazy. And then it went into the inside, the hollow, and produced a high pressure around palladium particles, nanoparticles, so-called palladium black. And then he took the gas out of the bottle afterwards, and if he used light water, had no deuterium, he saw no signals in the mass spectra. So these are repetitive mass spectra done sequentially, and they're done with high enough resolution to distinguish two things, a helium-4 and a deuterium, that are almost the same mass. So he had enough resolution. So he sees nothing if he doesn't have deuterium. And then in the deuterated samples, he sees not only the deuterium that was put in, but he sees the production of helium-4. Okay? So again, here is a nuclear transmutation happening on a tabletop in a low-voltage experiment. Okay? It's very significant, very important. Now, closer to home at SRI International in Palo Alto, California, Mike McCoubrey did an experiment where he had a vessel and he put deuterium in it with palladium, finely divided palladium, and he draws off samples as time goes along. So here's the time during the experiment, and you see the data here, various data analysis methods. Again, I'm not going into it. So this is helium concentration vertically and time this way, and it creeps up and it goes above the atmospheric level of helium. It's 5.2 parts per million. In other words, it wasn't helium coming in from the atmosphere. You know, it was more than that. So then, at the same time, he was measuring the energy, so that allows him to make a cross plot of the helium increase from this versus the energy, and he gets this plot, okay, by two different analytical methods, the green and the blue. I'm not going to talk about that. If you look at the slopes, you see in black 31 plus or minus 13, 32 plus or minus 13. So he gets about 31 or so MeV. Now, in that very rare 10 to the minus 7th branch of conventional DD fusion, you got 24 MeV gamma ray. Okay, so here's an energy that's sort of in the ballpark. Oh, and maybe not all of the helium was captured. You know, maybe some of it stayed in the metal. Okay, so the denominator would be small, this ratio would be large. In any event, this is a very, very good group doing a very careful experiment, calibrations, levels above atmosphere, and a tight helium heat correlation. Okay?
While you're on the slide, could you speak briefly about the time periods we're looking at here and how that is in some ways some of the problems that are seen people who look at this? I mean, if I look, that looks like a time scale of days across the bottom of this experiment.
Yeah, I appreciate that observation. A question is, you strike a match, you have heat. How fast do LENR experiments turn on? The initial Fleischmann-Pons experiments took weeks and even a few months. Okay, here you have an experiment that took, you know, sort of a week before it really, really took off. But having said that, there are some experiments in the field that take off immediately. Okay, and I can cite them. A fellow from California, Mel Miles, does a particular electrochemical experiment, and he sees evidence of excess heat within the first day. Okay, but that remains an issue. Okay, so you can fairly ask me, what don't you know? Well, I don't know how to trigger it. I don't know how to make it happen every time. I don't know how to reproduce it. I don't know how to control it. I mean, we got a ways to go in terms of commercialization. But the gestation time, the trigger period, has been and remains an issue. Now, Ed Storms, formerly of Los Alamos, took 16 papers where both the heat and helium were reported. So he made a ratio of the number of heliums per measure of the heat, and he gets a histogram like this. Now this is the value of the 24 MeV per particle that comes out of standard DD fusion. So you back off and look at this and you say, it's not right on. Okay, maybe it's something else. It's not hot. It certainly isn't hot fusion. Temperatures aren't there. The neutrons aren't there. Okay? But there's an element of reproducibility in this field. Okay? I mean, these experiments were done in diverse labs around the world, and yet they produce a fairly tight distribution. You know, not iron, not, you know, a single bar, but a tight distribution. Okay, so that's helium. Now I'm going to show you one, excuse me, very bad slide on other elements, transmutations. So experiments were done, the one on the left, George Miley at Illinois, the one on the right, Tadahiko Mizuno in Hokkaido in North Japan. So they did very different experiments. This was a fluidized bed reactor. This was an arc discharge in heavy water. Very, very different experiments. Different places, different people. Then they plotted the increase mass by mass by mass by mass across the periodic table. So they measured the elemental concentration before and then measured it after. 4 different techniques at both places, 3 of them in common, 1 was different. Okay, they get all this data and you back off and you look at it and say, there seem to be peaks. Okay, peak, 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 peak. And I put the arrows at the same atomic number values in both data sets. Okay, so they line up. And I remember my visceral reaction when I saw the second of these. I had seen Mizuno's data in 96, and when Miley presented his in 97, I said, holy cow. I'm sitting in the audience at a conference, and I said, that's like Mizuno's data. So a fellow in Switzerland and I did a statistical analysis of these, and indeed there are, you know, statistically correlated. Now, Ed Storms, the guy who produced the graphic that I showed you a moment ago, reads the literature and he says, let's count the number of papers that report the production of magnesium, the production of aluminum, the production of titanium. And you get peaks and they line up too. I didn't line them up in this graphic properly, but nevertheless they lined up. Okay, so you say to yourself, let's see, you're doing an experiment. You take palladium, interact it with deuterium, and you get iron, and things like this, copper, zinc. Yes, the possibility of fission following one of these LENR reactors is in play in the field. Do we understand it? Not a chance. We're nowhere near it. You know, we have nuclear theorists who work on this, but they don't understand it yet. Okay? Very, very interesting data. Okay, so I've showed you the transmutation data, tritium, helium, other elements. Now let me go into the thermal energy, far outside what can be produced by chemistry, indicating the reality and the practical potential. Okay, so I'm going to show you another set of data view graphs on heat production. Okay, so before I get to that, I remind you of the basics of both chemical and nuclear reactions. You put reactants and an initiation energy into the proper conditions to get out products and energy release. This is prenatal reaction science. You're born knowing this. It's so basic. Okay, so what do we have here? We have a plot of energy versus reactants and the products. There's a transition state here. And I ask you, okay, let's talk about the chemical case first. Why are you not on fire? You have combustible clothes and a sea of oxygen. Okay, and the answer is there's a barrier there, an activation barrier. And what is the physics? It's this chemistry of that activation barrier. You have to take the molecules, disassemble them, that takes energy, and then reassemble them into products. Now when you go to the nuclear case, you're not reassembling atoms in molecules, you're taking 2 positive charges and trying to slam them together, the so-called Coulomb barrier, and that's the thing there. Now the salient fact is that for the chemical case, the size of the transition is a fraction of the energy that you get out. For the nuclear case, the size of the transition is a fraction of the energy that you get out. One case on the EV scale, one case on the nuclear scale. Okay, so I told you, my pop quiz for you, if I run into you again, is what's the most important fact in this field? And it's the ability to generate nuclear reactions using chemical energies. Well, if you can get a megavolt out for a 1 EV investment, you have the possibility of a gain of $1 million. in principle. Well, wait a second. There's statistics involved and so forth. Okay, so then I have a question from the back. What's the biggest gain that's been seen so far? Ratio of thermal out divided by electrical in, 800. Has it been reproduced? Not even close. Do we understand it? No. Emphatic, as in hell no. Okay, so the big gains have been reported. Now, I'll show you data in a little while from an Israeli lab where there's a gain of 26. Okay, now I don't have a view graph on this, but let's consider our coal-fired power plant. 1 unit of chemical energy, then you turn it to thermal energy and you lose out, and then you turn it to mechanical energy and you lose out, and then you turn it to electrical energy and you lose out. You get, what, 40% or so of the, thank you, 33%, of the starting energy. But I'm telling you that this field holds the promise of not going that way, but going that way, and then dealing with thermal and Carnot and insulation and friction and other losses. Okay, so I'm trying to make sure that you see the high-level picture. Okay, nuclear reactions with chemical energies and gain is the second big thing that I'm trying to get across. So now we're going to look at some examples of data. This was from a Fleischmann-Pons patent in 1990. I found this graph by going over the Patent and Trademark Office in 1990. And they plot time this way and temperature in their cell this way. And these dips are half daily additions of makeup water. Again, D2O to make up for the electrolyzed water. So they dumped it in and it gets cool for a moment, okay? And then one day, the temperature jumps up 10 degrees after one of these additions. And it takes a different slope and it starts to go towards boiling, that yellow line. And then another addition, it drops down to the baseline, okay? Now, you have a choice here. Fleischmann and Pons, two respected chemists, okay? Could they measure temperature? This is not a complicated measurement, for Christ's sakes. So there was a choice. Either this is real data or they're liars. They made this up, okay? And that's basically the situation you're in. Okay, so as early as 1990, this kind of data was in play. Okay, I'll show you some more. Now, this and the next view graph are sort of a nuisance because they're very complicated, but let me walk through it. Parametric studies. Scientists, you vary parameters, you see what happens, okay? So Makubari at SRI and Kunimatsu in Japan did experiments where they varied the number of deuterons that had been soaked into the palladium. So you ratio the number of deuterons to the number of palladiums, and then you measure the excess heat, or vertically. Okay, so here is 0, horizontal in both cases. Here's 0.85. That 85% of the palladium atoms had a nearby deuterium atom. Okay, heat takes off. The data, they're not in perfect agreement, but here you had two experiments, one from 92, both of them from 92, that showed that if you increase the loading, it's called, the ratio of deuterons to palladiums, you will get excess heat with a higher probability, okay? Now, this, in a similar fashion, people varied the current flowing, the milliamps of current. So here is work, again, from Fleischmann, this time from Fleischmann and Kunimatsu, same time frame. So here's power, watts per cubic centimeter. This is also watts per cubic centimeter. And this is milliamps per square centimeter of the cathode, the palladium rod that's in the experiment. Okay, it's a measure of the current density. This is 10 to the 2, 100 milliamps per square centimeter, 10th of 100 milliamps per square centimeter, takes off. Okay, so we had, you might say, confirming data on the importance of a parameter, milliamps per square centimeter, in electrochemical experiments as early as the dates that you see on this graphic. Now, I had mentioned Arata already. He and his colleague, Chinese colleague Zhang, did an experiment. That's most of a year, horizontally at the top there, and they put their data out as kilojoules per hour, so energy per time, it's power. Kilojoule per hour is about a quarter of a watt. And if you sort of draw a line through there, it's maybe 30 or 40 kilojoules. So they got 10 watts of excess power for most of a year, okay, in an experiment. Okay, 10 watts, that's not a lot of power, of course, but if you think back to the history of the transistor, first transistor, big clunky thing, intermittent operation, people didn't understand that sodium was an impurity that killed the behavior of silicon and so forth. So you can look on this data as the data that was taken in the early stages of the transistor. If we had funding to pursue this, then we may be able to get the control that we need, understand the variation. You see there's an arrow here, break of the water and electricity. So they had the experiment running, it looked going up, 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 and then power went off, dropped down, started up again. Very enticing data, but from a practical viewpoint, only enticing. I mean, you can't make a generator out of this, okay, in any realistic fashion. So there's additional data in the bottom I won't talk to. Now the Israeli, oh, sorry, I forgot this one. Another view graph that violates the rules of making view graphs. Mitchell Schwartz, Boston area, a radiologist, a real doctor, okay, a PhD, EE from MIT. He does experiments in this area. So he had 2 experiments. He put the power in. One ran through a control. The power ran through the control. Then the second experiment was what he calls a fuser. So let's look at the control first. You see up on top, power in, power out, the integrated values. He knows how to do power and energy measurements, as demonstrated by his control system. Okay, so let's look at the data, this 15-hour period. Fuser power in, the pink, the fuser power out, the red. So the 2 diverge, making energy. Okay, and at the end of the experiment, he turned it off, and he still got power out. So the HAD stands for heat after death, after the death of the cell, after it was turned off. Okay, strange name, but that's what's used in the field. And there's a little incremental increase in energy, okay? So that phenomenon of a cell continuing to produce power, is it burning? No, but it's continuing to produce power after it's been turned off, has been seen in several labs around the world. Okay, so now, finally, this is the Israeli data. They were doing an electrochemical experiment. You see the time scale on the top there, running along, black input power, running around less than a watt, you know, rattling around. And all of a sudden the experiment takes off and starts producing that. You integrate under the ratio is 26. 26 units of thermal power out for 1 unit or per unit of electrical power in. That's very enticing. Now come back to the US. This is data from the Naval Research Lab saying it's kind of a thing. Power in, red is the power out. The peak power gain at this point, that is the red divided by the green, is like 40. The integral for the entire experiment beyond what's shown on this graphic is 6, okay? How would you like to be able to take the electricity that you get, multiply it by 6, and reduce your bill by a factor of 6? That's what's in prospect, okay? So this gain business is really, really, really important, and that's why I give it the emphasis. Okay, now, theories. I'm done showing you complicated view graphs with data that I don't spend enough time on. Okay, now let's talk about theories. Dozens of theories. Most of them are very incomplete. PBIs, partly baked ideas, okay? People would say, I know how it works, and then they have steps to do. Write down the equations, evaluate the equations, compare it with the experiments, predict the experiments, design the experiments, okay? Hasn't been done. 1994 hasn't been done enough, some, but not enough. 1994 review, there were already 25 LENR theories out, and this paper was written and you know, basically panned them all. None of them were adequately complete as a scientific theory in order to compare with the experiment. Okay, I just finished a paper called Expectation of LENR Theories. You know, beware, I'll send you a copy if you flinch. Anyway, there's a lot of information, a lot of references on there. Okay, so I have a lot of friends in this community who are theoreticians, okay? And, you know, they will start out with an idea, and I will liken it to the following. They will put an idea out, and then they'll work for years, sometimes decades, on the consequences. And the initial assumption is so bad. I tell them, and they don't like this, but I tell them, okay, I've been commuting into Washington for 55 years, okay? Work at the Navy lab, work at the university. Let's assume I can fly, and then work out the details, how that affects my commute. You know, come on, people. It's, you know, they generally tolerate me because they know that there's a problem there. I don't have my tires slashed or anything. Okay, so finally we come to the second part, prospects for commercialization. As I say, that's a very, very strong driver. Now the Anthropocene Institute is led by a guy named Carl Page. You may recognize the name. His brother founded Google. Okay, so he has this institute, and one of his main interests is LENR. So they put out this 75-page report listing dozens, you can read it, companies, organizations, yada, yada. And that's where I got the number that 20-plus companies are working on LENR. Okay, so this report is available. It's on the web. Okay, so what has to be done for commercialization? You're rich. LENR scientists come to you and say, I want $5 million. I'm going to start up. I'm going to develop a generator. So what are the questions you have to ask? Well, show me something that's reproducible, controllable, and reliable, which is an absolutely fundamental requirement for a product. And then, by the way, if you look at product development, it takes like 18 steps. Okay, I have a paper. I list them if you want. Okay, a lot to do. Now, regulatory approval is hard to know. You've got 3 levels of government: local government, state government, national government. There's the N word, LENR, nuclear. Remember the story of MRI. What is magnetic resonance imaging? It's nuclear magnetic resonance. But when they made the images, they weren't going to put the word nuclear in. Here's grandma going down to get subjected to nuclear reactions. No way. Okay. So anyway, there's a big uncertainty about what's going to happen when this gets to the point where you actually try to bring a product to market. Customer acceptance is unknown. I mean, what if there's an explosion and it happens to be an electrical explosion or something? It has nothing to do with LENR. It could still get a bad name and have a real problem in the marketplace, despite the fact that it could be cost effective. And the biggest wild card is when LENR will be understood, because if we had the understanding, we undoubtedly could commercialize things much faster than we have been. Now I'm going to show one view graph on civilian applications and a couple of view graphs on military applications. So we live in a world, increasing population, increasing per capita use as nations develop. Massive burning of coal, oil, and gas seems to be affecting the climate. I don't want to get into an argument over that, so I softened the wording. Okay. And LENR gains foretell very cost-effective energy production. It doesn't produce prompt radiation. You can stand next to an experiment and you will not be damaged. You take sensitive radiation detectors, gamma ray detectors, neutron detectors, ion detectors, whatever you want. There's not much coming out of these things. They're fundamentally radiation safe. Oh, and by the way, they don't emit greenhouse gases. Okay? So LENR generators, if developed and accepted, could be widely distributed globally in all kinds of countries. Now, pop quiz. How many people in the world don't have clean drinking water? Rough number. Pardon? 1 billion, yeah, raw numbers. 1 out of 7 people in the world don't have good drinking water. Do they have diseases because of that? Of course. What if we had an energy generator, kilowatts, that would allow desalination or cleaning up river water? Okay? Dramatic effect. Okay? And in fact, we just finished a paper on that application of LENR. Stay tuned. Okay? Now, I worked for the Navy for a long time, and I'm trying to sell the DoD on funding LENR. The U.S. military would benefit greatly. Small LENR generators, both in fixed installations and forward deployments. Fuel for use on the battlefield is incredibly expensive. If you want to have an upset stomach, look at what the DoD pays for fuel. Think of aviation gas on a carrier in the middle of the ocean. It's really, really, really expensive. So generating heat and electricity in the field, in a forward deployment, without a fossil fuel logistics tail would be very, very important to the Marine Corps and the Army. And this admiral came to our university to give a talk a few years ago. I went up to him afterwards. They said, I used to work for you for ONR, and I'm working on cold fusion now, I said. And he said immediately that would be a game changer. No hemming or hawing. He knew about it, and he knew that if we could pull it off and commercialize it, it would really, really make a big difference to the Navy. Okay, so when I graduated in 1960, my first job was as the admin officer and navigator on that ship. So I navigated that ship around the world with a sextant in my hand, made it back to the same port, I say with pride. Okay? So we went down the island, we tied up there, and we offloaded clothing and food and energy, as I'll get to in a moment, scientific instruments, medicine, Playboy magazines, everything. Okay, we took it down. So we were tied up with the ice and we'd offload it. And that was a proper scan. I just took these pictures quickly from the slide to prepare for this talk. So those are barrels of oil. We would go up to near Providence, Rhode Island, We'd spend a week, barrels of oil, onto the ship. Then we go down to the Antarctic, spend a week, barrels of oil off the ship. Okay. In 1962, breakthrough. We took a nuclear reactor made in Baltimore to power the McMurdo station south of New Zealand. It ran the station for 15 years and then was replaced by barrels of oil. Okay, so I was signed for the Corps. It was an interesting situation. Okay, so that's 1962. Let's flash forward half a century to a DOD report on energy for the warfighter, operational energy strategy. What are we doing? Pushing barrels of oil around. Okay, at great cost. Okay, so here you have a situation where the DOD has half the research money in the U.S. and has this problem, and we can't get adequate funding. Okay, the Navy, okay, I'm Navy-centric like Professor Beach. Major contributions, the SPAY War, it's called Space and Naval Warfare Laboratory in San Diego. 48 refereed papers on that website. Many papers from the Naval Air Warfare Center in China Lake, Naval Research Lab, and there are current experiments going on at a Navy lab near Washington in Dahlgren. Okay, so it happens that the Navy's been very active in this. I'm almost done. What am I doing about it? I have a lab at the George Washington University. We're doing loading experiments, take a piece of palladium, load it with deuterium, or we're doing what are called co-deposition experiments. The trouble with buying a piece of palladium is that you're stuck with whatever impurities, whatever structure is in that piece of palladium. So an alternative is to make your own by depositing it chemically, electroplating it out. At the same time, you put the deuterium in it. That's the co-deposition part. So we're doing heat measurements, thermometry, and imaging, infrared imaging. We'll do calorimetry when we think it's ready. We have various spectroscopic techniques and so forth. And of course, our eventual goal is to understand and exploit LENR. But the first target is to understand our experiments. So we're doing measurements, we're doing simulations, different kinds of experiments, and so forth. Okay, I could go on and on, but let me let it go at that. So to wrap up, there's a twofer here. I'm 4 months away from turning 80. I am having too much fun to retire. I'm working on a good scientific problem with real practical promise in the company of interesting people, including in this room, Carter, and I'm going to stay with it as long as I can. Will I ever have one in my basement? No, I'll be gone by that time. Will I live long enough to understand it? Maybe. Maybe somebody has already seen key insight and is going to publish tomorrow what the answer is. Maybe. I hope at least to live long enough to turn this into a legitimate area of scientific inquiry funded as such scientific areas are by the U.S. government and others. China's funding it as an aside, Chinese government, okay? And that's something I'm working on in a very vigorous fashion. So the last thing I would say, and again, thanks for the chance to talk with you. There will be an international conference on this subject in Colorado State University, Fort Collins, Colorado, the first week of June of next year. That was just determined. It'll be announced today or tomorrow publicly, so this is a sort of a sneak preview. And if any of you are interested in this, I'd be happy to see you. We're going to have a student scholarship program that'll be advertised too, so you could apply to that. And for those people who are selected for that program, if you show up at the Denver airport, you will get transportation to the conference. You get to live indoors, you get to eat, you get to go to the meetings, you get the handouts, you get the conference banquet, you get the excursion, and transportation back to the airport for free if you qualify. So if any of you are interested in this area, undergraduate or graduate students, get in touch with me. You know how to do that. So thanks for your attention. I would be happy to take complaints and criticisms and other problems now if you like. Appreciate it.
Thank you, Dave.
Thank you. Now the fun part. This is the part I like.
Hello, thank you so much. I really don't know much about this technology at all. So I was hoping you could go through and clarify some of the experiments that were being done. Specifically, you have the palladium and each day you dose it, or at even increments, you dose it with the deuterons. So is it you have to like add in extra material at some sort of schedule, correct?
Yeah. I apologize for not making that clear. So imagine a beaker, and you've got a piece of palladium, and then a counter electrode, commonly platinum because it's not reactive, and it's immersed in an electrolyte that is a solution of a salt in heavy water. You apply a voltage, it decomposes the water, and the deuterons interact with the palladium. Sorry, I didn't make that clear.
Oh, so you don't need a consistent like dosing of like, you don't need like an external dose of.
No, you get your deuterons by breaking down heavy water.
Okay, so it's something that could, you could create this type of energy in a closed loop, correct? Is that the?
Yes, and in fact, if you can take an experiment and get out so much more and then run an electrical generator, back. So there are people in the field who have very, very high standards. They say the only way that we can convince people that this is real is to have a self-sustaining experiment of that type. Okay, I don't agree with them. I think that it ought to be possible to convince people by showing them data such as I've showed you. Okay, but some people want a self-sustaining situation. Thank you.
Thank you.
Hi. In one of your slides, you said something like, if this technology is developed and accepted, and well, the thing is, you told us all the good thing about the technology, so I was interested in the accepted part. So I assume that if you said that, it's good because it doesn't have, for example, greenhouse gases emissions, but I guess there is something that is not that amazing about it?
Well, that's a very good question. You might say, I just listened to a salesman for an hour. Okay, because I'm talking about no prompt radiation, no residual radioactivity, no greenhouse gases, energy gain, and these good things. It's possible that a downside will develop, but the fuel is not a complicated material. It's not explosive. It's not flammable. Okay, what comes out of it, isn't dangerous. Okay, so this looks like I have friends who say, God screwed up. This looks too good to be true. Okay, but we don't know for sure of a downside yet. Now you can say, you got to manufacture these, and they've got to be, maintained. You need people to keep them running. Fuel replacements. You have to dispose of them properly. But that's true of our refrigerators and other things. Okay, so this looks like something that could have a historical impact. Okay, and I have stated in writing already that if this is understood, reproduced, controlled, commercialized, and so forth, this could have an impact in the energy regime that the transistor did on computations and communication. Now, you're free to argue, laugh, whatever, but that's my opinion after looking at this for a long time. It really looks like it could go someplace. Okay, so thank you. Sir?
So I think most of your charts seem to show temperatures below 100 degrees C, and you're talking about a self-sustaining reaction, and you're comparing heat out to electrical input energy, which means if you want to use the heat output, you have to be able to convert a low temperature difference to electrical energy to then self-sustain itself. So let's just say that it was all proven. Everybody was like, I can reproduce this, and I can always get 70 degrees centigrade.
So what?
So
Yeah,
So we have hot water baths. We can do some cooking, and the question, can we actually generate power?
Yeah.
Is a different question.
Yeah. No, this is a good audience. Your questions are very, very bang on. I didn't go into this. I mean, on one slide I showed you can use palladium and deuterium, or you can use nickel and hydrogen. Okay, so the field is bifurcated essentially into the people who are using electrochemical approach. And the reason that's worth doing is because you get a lot of deuterons out of electrolyzing water. If you calculate the rate at which the deuterons are going into the palladium, here's one lattice cell, on the surface. 75 deuterons per second go through that, going into the palladium. Okay, you get a high effective pressure. Okay, but in terms of commercialization, you are absolutely right. Low temperatures are not a good way to make electricity. So the other side of the field is using nickel with hydrogen gas at high temperatures. Okay, and experiments are commonly done up to 1,000 and 1,200 degrees, and people see excess heat production. So the expectation is that the classic palladium, deuterium, electrochemical side of the field is great for science, but when it comes to commercialization, it's going to be hot nickel hydrogen experiments. Okay, and there's a big database on that already. Great question. Thank you. Sir.
What kind of equipment or characterization do you think is needed for reveal the nature of the reaction?
Yeah. Well, very broad question. In order to do an experiment, you have to have equipment to power it and then equipment to record data. Okay, and in fact, I was at National Instruments today talking to them about this because they manufacture equipment on both sides of it. Okay, but the other part of your question is, okay, it's materials that matter. You know, why do people take one batch of materials and get positive results and then go to another material and get nothing? So there's some aspect of materials, impurities, structure that we don't understand. So the whole zoo of material analysis tools for both composition and structure is being brought to bear on the materials that go into the experiments and the materials after the runs. Okay, and X-ray diffraction and ICP, inductively coupled plasma mass spectroscopy, SEMs, EDAX, yada yada. Lots and lots of techniques are being used to characterize the materials before and after the experiments. So I told some of you, I spent 20 hours in the last 3 weeks on a scanning electron microscope at our place looking at the materials that came out of an experiment.
I feel like if people really want to know the atomic reaction, people need the atomic level facilities to see how the atom trap the proton or some other trap.
Well, yeah, so, most of you probably know it's possible to see atoms now. You can do that in a transmission electron microscope, but more commonly it's done with atomic force or scanning tunneling microscopes. So let us count the number of experiments in this field where people have used an atomic force microscope to look on an atomic scale at a material before and after an experiment. I know of one paper. Has anybody done it in situ? You can run atomic force microscopes wet, put them in an electrolyte. Zero work. Zero work. So, there's this cliche, the closer you look, the more you see. It is very, very possible that this field will not be cracked. We will not understand it until we have data at an atomic scale. We'll see.
One thing he hasn't said, that's a very expensive experiment.
Yeah, and that's part of the problem that, we just don't have the funding, okay, collectively.
Thank you. The basic question I had was, if so many people have data, why is nothing reproducible? What are the main pitfalls for reproducibility?
Okay, so it is not true that nothing is reproducible. There are some experiments are close to 100% reproducible. This man Miles, I mentioned him in passing, has done 11 experiments with a particular palladium boron alloy. 10 of the 11 times he got excess heat. The last time, the last one, the 11th time, whatever sequence it was, had a cracked cathode. So it was understandable why that one didn't work. So there are some experiments that are quite reliable, but globally they're not reproducible, especially when somebody does an experiment one place and then somebody else does the same experiment. That's why I showed that parametric data on milliamps per square centimeter and loading, because here you had the same answer coming out of two very different experiments in very different labs by very different people and so forth. Okay, so there are some experiments that are relatively reproducible. So they say, okay, fine, Miles' experiments are reproducible. How much power does he get out? Half a watt. Half a lousy watt. What's the signal to noise? 10 to 1. It's plenty good. It's good data. You can't dismiss it. On one hand, but half a watt isn't going to carry the day. So there are no experiments that are reproducible that give relatively high powers, 10 watts or more. Okay? Now, there are experiments, from China and other places that have reported 300 watts out of power and so forth. So it's not that there are none, but they're not adequately reproduced. Okay. So if you go out of this talk thinking that it's an interesting subject, then I've done my job. If you go out of this talk thinking that guy's having fun, done my job. Thank you very much.
Okay, thank you again, Dave.
And again, anybody interested in calendars, help yourself. I brought a few.
And again, if any of you would like to join us, we're going to walk over to Gabriel's at the AT&T Center for some adult beverages or non-adult beverages and some food afterwards. So you're more than welcome to join us if you'd like to continue the discussion. Thanks for coming.